Welcome everybody to the first official video from Montwell Tutoring, and I'll be going through exponents and explaining the basics from A to Z. So I'm going to be going over the first episode right now in this video, but in the next little while I'll be creating a playlist which you can watch on your own time and back to back to back the full understanding of exponents. So without further ado, here we go. Exponents are composed of a base. So here I have my base, and then we have the exponent itself. And here I'm just using b for base and n as in any number for the exponent. Now, as we delve deep into this, we will experiment with variables in the place of n, variables in the place of b, but we'll start real easy. We'll start with our first step. So if we have, for example, 2 to the power of 2. What we do is, first we write that it's equal to 2 times 2. So what we're doing here is we're putting the base, multiplying it by itself, by the number up here, the exponent. So, as another example, 2 to the power of 3 would be 2 times 2 times 2. So here we have 1, 2 terms. Here we have 1, 2, 3 terms. All right, and of course, if we increase that number, 2 to the power of 4, we will repeat the same pattern. Now, does the law change if we change the base? No, it does not. So, 3. So if we have a base of 3 and we have it squared, or in other words, to the power of 2, it'll be equal to 3 times 3. If we have 3 to the power of 3, it'll be 3 times 3 times 3. If we have 3 to the power of 5, it'll be 3 times 3 times 3 times 3 times 3. Essentially, 5 times 1, 2, 3, 4, 5 terms for the fifth exponent. All right, so if we evaluate them, we can do, 5 to the power of 2 gives us 5 times 5. Now, what is 5 times 5? That gives us 25. If we have 2 to the power of 3, we have 2 times 2 times 2. That'll be equal to 2 times 2 is 4, times 2 is 8. So we're left with 8. Now that we understand the concept of the exponents, we can work out some operations. So the first operations we'll go through with are additions. So when we're adding exponents or exponent form equations, for example, let's say I have 2 to the power of 2 plus 2 to the power of 2. Now the easy way to do this is to simply elaborate on each one, then evaluate it all together. So separately, we have 2 to the power of 2, that's 2 times 2, plus another 2 times 2. Each one is, here it's 4, here it's 4, 4 plus 4 gives us 8. All right, easy enough. Let's switch up the numbers. Maybe an equation where they aren't the same base. Let's say we have 3 to the power of 3 plus 5 to the power of 2. In this case, I'll do the same thing. 3 times 3 times 3 plus 5 times 5. 3 times 3 times 3 gives us 27, because 3 times 3 is 9. Multiplied by 3 again gives us 27. Then we have 5 times 5, which is 25. Now all we have to do is add them up. So I know that 7 plus 5 gives me 12, and 20 plus 20 gives me 40. So I know that this gives me 52. All right. Now, the rule doesn't actually change for subtraction. If I have 2 to the power of 2 minus, let's say, 3 to the power of 5, I will still be evaluating each one separately, then doing the operation. So 2 times 2 minus 3 times 3 times 3 times 3 times 3. A lot of 3's. First one gives me 4. This one is 3 times 3, which is 9. This one's 3 times 3 equals 9. When I multiply 9 times 3, that gives me 27. Then I pull up my trusty calculator, and I do 9 times 27, and I get 243. All right, that's for the first one. Or let me go back with this. Okay, so I have 27 here. I have 4 minus the answer, which was 243. All right, that's a pretty big subtraction here, but I think we can handle it. What we're left with is minus 239. So, as we see from both examples, all we do is we elaborate on each exponent form, then we evaluate it. Easy enough. All right, how about we work with some multiplications? Naturally, that's the next operation. What if we have 3 to the power of 4 times 3 to the power of 2? Now here there's an important tip, and the tip is the bases here are the same. And when the bases are the same, we can maintain that base at the end for the result. Now, bear with me here. For the exponent, that's the part that will change. When we are multiplying in the operation, we add the exponents. So I do 4 plus 2, and that gives me 6. So the exponent here is 6. Now I can elaborate on this. I can do 3 to the power of 6, 3 times 3 times 3, times 3 times 3 times 3. Now using my calculator, I will get a total of 729. Now, what if I did this separately and multiplied them, just to see if this were really true? 3 to the power of 4, that gives me 81, times 3 to the power of 2, which is 9. Plug it again, 81 times 9 gives me 729. So now we know that for sure this law works. Okay, let's do another example. What if we had 4 to the power of 2 times 4 to the power of 4? It is still as easy as adding the exponents. And the condition is that the base is the same. Since it's 4 here and it's 4 here, I can simply add the exponents when I'm multiplying them. So what do I get? I get 4 to the power of 2 plus 4 equals 6. So it's 4 to the power of 6. And when I plug that into my calculator, I get a pretty big number, 4,096. All right, what if we have situations where we're multiplying exponents with different bases? So we've used the 3 as a base, the 4 as a base. What if we have different bases? What if we have 2 to the power of 2 times 4 to the power of 3? Since the bases are not equivalent, because 2 is not equal to 4, we cannot use the rule. You cannot use the rule of adding the exponents. What we have to do now is do them individually. So we get 2 times 2 for the first one, times the second one, which is 4 times 4 times 4. This one gives us 4. This one gives us 4 times 4, which is 16. Then we do 16 times 4, and we get 64. So we have 4 times 64, and the grand total is 256. So in this situation, we had to separate them. We were not able to do it as simply as when we had this exact same base. Simple enough. Let's do one more example just for review. We have 3 to the power of 2 times 2 to the power of 4. We simply do them separately, which means we do 3 times 3 first, times 2 times 2 times 2 times 2. The first product gives us 9. The second product gives us, this one, 4 times 4 is 16. Now when we multiply 16 times 9, we get 144. All right, now let's move on to our final operation, division. So in division, it's going to work a little similarly to the multiplication. What we're going to start with is exponents in forms where the bases are equal. So this operation of, let's say, 5 to the power of 6 divided by 5 to the power of 5 is equal to, recognizing that the base here is the same, I can write 5 as the base of the quotient. Then for the exponent, I do 6 minus 5. So I do 6 minus 5 is equal to 1, and I get 1 as the exponent. Now, as you may have already known, 5 to the power of 1 is equal to 5, because we're multiplying 5 by itself one time, so we just leave it as 5, meaning that the end result here is 5. All right, what if we change up the numbers? What if we have 2 to the power of 3 divided by 2 to the power of 1? Here, since we have the same base of 2, you write that the quotient has a base of 2. Now for the exponent, we do 3 minus 1. That gives us 2. Therefore, it's 2 to the power of 2, which is 2 times 2, and leaves us with 4 as our final result. Now, are there any more applications of such rules? Are there some interesting exceptions that we should be aware of? Or maybe some special ones that we should be aware of? Of course. First thing is that when we have a base of any number, let's say we have a base of 5, and it's to the power of 0, it is equal to 1. Now, what if we have 5 to the power of 1? As we discussed earlier, that gives us 5. Now, what if we had a situation where we had 5 to the power of a fraction, like 1 over 2? That would give us a square root. In this situation, because it's 1/2. We will discuss this particular example, in a future video. But for the time being, we don't have to focus on these ones. Next, we have 5 to the power of a negative number. We will also dive deeper on what this exactly means in a future video, but for the time being, know that it means 1 over 5. And what this could indicate is that if we changed it to 5 to the power of negative 2, we have 1 over 5 to the power of 2, meaning that the negative number simply brings the number here, the base, into the denominator, and gets rid of the negative sign, meaning here it's positive, and we have the same exponent on the denominator. So if I have 5 to the power of negative 4, it'll be equivalent to 1 over 5 to the power of 4. And the higher, or I should say the lower the number here is, so if it's negative 90, for example, the smaller the answer is, because it's 1 over that number, meaning it's always going to be a smaller chunk of the pie. Alright, I hope this video was useful to you as to understand how exponents work, and I hope to see you in the next video.